Okay, so we did these questions last time, covering joint densities, transformations, minimax, order statistics, and so on. So here's the next question in our discussion. Okay, so since you already seen this one, I'll go quickly. I hope you have looked at these questions earlier. Okay. Now you have a die. Now it is not a balanced one. You know, if your die is a balanced one, all 6 sides, they have the same probability of being selected, right? So that means the probability of selecting 1 is 1/6, 2 is 1/6, all the way up to 6. All these 6 sides, they will have the probability 1/6. That is only if the die is a balanced one or a fair die. Now in this question, our die, it's not a fair die, it's unfair die. It's an unfair die. It lands on each of the odd numbers, you know, the odd numbers 1, 3, and 5. The probability is C. Okay, getting odd number is probability of C, and on each of the even numbers, that means 2, 4, and 6, that is twice, 2 times C. Okay, now you can see the difference between an unfair die and a fair die. So not all these phases have the same probability. Okay, it is actually loaded towards, or it's biased toward 2, 4, and 6. It's twice, right? The probability of getting 1, 3, or 5, they will be probability C, but 2, 4, and 6, 2 times C. Okay, so it is an unbalanced or unfair die. So the first question is you have to find C. So how do you find C? Now this is about the in order to have a distribution, a valid probability distribution, you know, all possible x's and then their probabilities. After you identify them, the total probability should add up to 1. So that is the condition that you have to use in order to find C. Okay, so let's write them down. The possible values of x, okay, so they will be 1, 2, 3, 4, 5, and 6. Well, if you can clearly see and understand the scenario, there's no need to write down this probability distribution also. Okay, you can just proceed with the values. But in order to explain it, I'll use this PMF, the table also. Okay, so it says the odd numbers, the probability is C. So this probability is C. And the even numbers, 2C. Okay, so here's our PMF. So if it is a valid PMF, what should happen? When you sum up these probabilities, okay, for all x, they should add up to 1. Okay, so let's see, you have C, how C there are 3 times and 2C appears another 3 times. So that will be 3C plus 6C, which is, it should equal to 1, right? So that's 9C equals to 1, which means C is 1/9. Okay, so the value of this constant C is 1/9. So what does that mean? Now you can write the probability of x if you want. So that will be 1, 2, 3, 4, 5, and 6. Probability of getting 1 is 1/9, 2 is 2/9. Why? Because it's 2C. Okay, so 2 times C is 2/9. Odd 1/9, even 2/9, odd 1/9, even 2/9. So that is our PMF of x. Okay. Well, you don't have to write down these tables if you can clearly figure out this equation. Okay, this if you can figure out this connection, that's it. Okay, so these are just extra information, but if you want, you can note them down also. Okay, right. So that's part A. The next is, now is this clear to all of you? Is this fine? How to find C? Okay. Right, part B, suppose that the die is tossed. Okay, now you are tossing the die. Let x equals 1 if the result is an even number, and let it be 0 otherwise. Okay, so now we are defining 2 more new random variables. What is x? X equals 1 if the result is even, and let it be 0 otherwise. So what are the possible values of x? It can be either 1 or it can be either 0. X will be 1 when after you roll the die, if the phase is even number, x will be 1. If it is an odd number, it will be 0. So 0 otherwise. Then you have another random variable y. Again, it can contain only 2 values, either 1 or 0. So y will be 1 when? If the number is greater than 3. Greater than 3, not equal, okay? Just greater than 3, and let it be 0 otherwise. Okay, so you have two random variables, x and y. They are clearly defined. They are possible values. And what are the meanings of these values? Okay, so they are nicely given. So the question is to find the joint probability mass function of x and y. Joint PMF of x and y. Okay, so when you have to find a joint PMF, you know it should be a 2D table, right? So let's say this is our x, this is our y. So what are the possible values of x? It can be either 1 or 0. Possible values of y, again, either 1 or 0. Now you have to find when you will get x1 and y1, and what is that probability. What are the situations where x is 0 and y is 1? What is that probability? So these are the 4 values that you have to figure out and identify. Okay. So let's try to do that. Anyway, when you throw a die, now these are not, there are no 2 dice, okay, just 1 die. Suppose the die is tossed. Okay, you just toss this 1 die, but there are 2 random variables associated with this single outcome. So what are your outcomes? Let's write down the outcomes. This is a 6-sided dice, so your outcomes will be simply 1, 2, 3, 4, and 5, and 6. That's all. Depending on the outcome, you can define what will be your x and what will be your y. Okay, what will be your x and what will be your y. Okay, and the probabilities of these outcomes. Now, shall we give another name? Let's say this is u. So pu is there. Okay, we already know that they are 1 over 9, 2 over 9, 1 over 9, and so on. Okay, now let's see what will happen if the outcome is 1. What is the value of x and what is the value of y? Can you find it? The outcome is 1. 1 is odd number, so it is not even. Therefore, the value of x is 0. Why? X is 1 if the number is even. But 1 is odd, therefore the value of x is 0. What is the value of y? Y is 1 if the resulting number is greater than 3. Is 1 greater than 3? No. So this is again 0. Now likewise, can you feel what will be the value of x and y if your answer is 2 after you toss the die? Answer is 2. What is the value of x? 1 or 0? The value of x is 1. Why? Because it is even. What is the value of y? 1 or 0? The value of y is 0. Thanks, Sarah. So why is it 0? Because it is not greater than 3. 2 is still less than 3. Therefore, this is 0. Okay, so likewise, let's fill. 3 is odd. Again, this is 0. You have to find greater than 3. So not equal sign is not there. So still this is wrong. Okay, so again, y is 0. About 4, it is even. So x is 1 and it is greater than 3. So that is also okay. So y is 1. 5 is odd. It is greater than 3. So y is 1. 6 is even. X is 1. Y is also 1 because it is greater than 3. Okay, so you have all these 0 and 1 combination. Okay, so let's fill the fill this 2 by 2 table. X is 1 and y is 1. How many possibilities are there? See, x is 1, y is 1. So there are 2 possibilities. So what is the probability? X1 and y1. You have to add these 2. 2 over 9 plus 2 over 9. So the answer will be 4 over 9. When x is 0 and y is 1. X is 0, y is 1. Where do we have x is 0 and y is 1? We have only 1. See, this one is when x is 0 and y is 1. So what is that probability? 1 over 9. Okay. Then we have when x is 1 and y is 0. X is 1 and y is 0. Use another color. So here's the one. Again, just one answer is there. X is 1 and y is 0. And what is that probability? 2 over 9. So there goes 2 over 9. And finally, we have 0 and 0. What are they? 1 over 9 and 1 over 9. Add them together, 2 over 9. Okay, so here's our joint PMF of X and Y. And if you add these probabilities, 4, 5, 6, 7, 8, 9, 9 over 9, total probability 1. So this is a correct joint PMF. Is this clear to all of you? How we figure out 1 1s, 1 zeros, 0 1s, 0 zeros, everything? Do you want me to repeat? Is it fine? Okay, I guess that's fine, right? Okay, so you have the joint PMF of X and Y. Okay. Next part, you have to calculate the covariance of X and Y. Covariance of X and Y. How do you find the covariance of X and Y? That will be expectation of XY minus EX times EY. Right? So that means you have to find expectation of the product of X and Y. The marginal, you need the marginal PMF of X in order to find EX. You need the marginal PMF of Y in order to find EY. Since we have the joint PMF in this 2 by 2 table, shall we find the PMFs also? It's very easy. So here comes the PMF of Y. That means when Y is 1, you add 4 and 1. So it's 5 over 9, 2 and 2, 4 over 9. If you try the PMF, the marginal of X, when X is 1, you have 4 over 9 and 2 over 9, add them together, 6 over 9, 1 over 9 plus 2 over 9, 3 over 9. So you have the marginal PMFs of X and Y. So we have everything in order to find EXY, EX and EY. Okay, so let's start with EXY. In order to find EXY, you need the joint probability, right? So how do you find EXY? Sum of XY, sum of X times Y times the joint density of X and Y. Okay. So how many combinations are there? We have 2 combinations. So let's try to find them. They will be X is 1, Y is 1, and its probability 4 over 9 plus X is 1, Y is 0. X is 1, Y is 0. That probability is 2 over 9. And when X is 0 and Y is 1, that probability is 1 over 9. Finally, you have 0, 0. Well, obviously, it's going to be 0. Anyway, all these values will go to 0. So we'll end up with just the first calculation, which is 4 over 9. Okay. Right. So that is EXY. Now let's find EX. That is sum of X times PX. X has only 2 values. It can be either 1 or 0. So when X is 1, its probability is X1 is 6 over 9. When X is 0, it doesn't matter. Multiplying by 0 will be 0 anyway. It will be 3 over 9. So EX is 6 over 9. And what will be EY? So rather than writing everything, you can easily figure it out. When Y is 1, 5 over 9 and 0, 4 over 9, it will be 0. It will be just 5 over 9. Okay. So we have EX, we have EY, we have EXY. So you have everything to find the covariance of X and Y. So let's substitute the values. EXY is 4 over 9 minus EX is 6 over 9. This is Y. EY is 5 over 9. We have 4 over 9 minus 30 over 81. Can you find the value and tell me the answer? Find the common denominator. Yes, so that will be 2 over 27. 2 over 3. So that's going to be 6 over 81. Should be 2 over 27, right? Yes, 2 over 27. You got it, Imangi. Okay, so if you want, you can leave it like this. If you want, you can simplify. It doesn't matter. Okay. Any of these answers will be acceptable. Okay, if you want to simplify this, I guess it is 0.0740. I guess this is correct. Anyway, you can leave the answer as a fraction or a decimal, simplified, doesn't matter. All these answers will be acceptable. Now in this question, it's not asking you to interpret it, but as statisticians, we usually interpret our results. So having a covariance, now this is a positive one. Okay, with the covariance, you can only explain the sign. Okay, because the covariance depends on the units. We cannot say anything about the strength. We can't say whether it is positive or negative, whether it is strong or weak or moderate. We can't say it. Only the correlation will give you an idea about the strength of the association. But the covariance, you can only tell the direction, whether it is positive or negative. In this case, we have a positive association between X and Y. There is a positive linear association between X and Y. So it's not asking you to interpret, but if you see the word interpret your result, make sure to write the interpretation also. Okay. So in our case, in this example, it will be a positive linear association between X and Y. Okay. And we move on to the next question. Are X and Y independent? Are X and Y independent? Justify your answer. Yes, how do you justify your answer? Usually when you have to show whether they are independent, okay, it's always good if you move on with checking the pairs of X and Y. Okay, you know how to check it. If X and Y are independent, what should happen? When you multiply the marginal probabilities, they should be same as the joint, right? For all pairs of X and Y, for all pairs, if at least one pair violates this condition, that means X and Y are not independent. Okay, so let's start with the first one, the pair 1, 1. So let's see, what is Px? When X is 1, 6/9. When Y is 1, 5/9. And what is Pxy? Where they intersect, it is 4/9. And you can obviously see that these two sides are not independent. So you can say X and Y are not independent. Okay. Now, if the covariance is 0, can you say X and Y are independent? If the covariance is 0, can you say X and Y are independent? Yes or no? No, exactly. Why? Because there can be situations where the covariance is 0, but still X and Y are dependent. Therefore, be careful. Now, this is a tricky question actually. Okay, now the covariance has a value, so that means they are independent. They are not independent. Okay, you can actually use that result from answer C. Also, you can say they are not independent. But you know, proving this, the marginal is not equal to the joint density is the best way to show the independency. Because, say for example, in part C you got 0. Okay, and mistakenly you said, okay, because the covariance is 0, X and Y independent. Can you say that? No. Okay, remember, when two random variables are independent, the covariance is 0. That direction is correct. Okay. And then, but the other way around, it is not always true. Okay. When X and Y are independent, the covariance will be 0, but having a 0 covariance does not say that X and Y are independent all the time. Okay, so I have to be very careful. And we have a question, can we use contrapositive statements of covariance of X and Y are not equal? Covariance of X and Y are not equal. You mean not independent, I guess, right? Because I mean X and Y are independent. Now, yes, in part C, since you have a value for the covariance, from that also you can say they are not independent. Okay. But just in case, if you got a 0 here, Okay, make sure to check this the pairs. Okay, so the first situation where you get this inequality for a certain pair, from there you can say that x and y are not independent. Okay, but if they are independent, all the four pairs should be should satisfy this condition. Okay, right. So that was one question. Okay, okay. Is it clear to all of you? So let's move on to the next question. Okay, so here you have two, one random variable y, actually x, sample of size 3, and their order statistics are there 1, 2, and 3. Okay, this is a sample of this is a sample of size 3. Okay, we have another question from the previous one. If the two samples taken from two dependent normal distributions, can we add means and variance of the two samples? For dependent, no. For dependent, no, because the variance will have a covariance term. When they are dependent, there will be a covariance. Okay. When they are dependent, the variances will have a covariance term. Now, I think you have got this twisted, because with the normal distribution, if the covariance is 0, the other direction is also true. I think that is what you have mistaken, Rosula. Even the normal distributions, if they are dependent, there will be a covariance. Okay. Now let's go back to the previous example. I said that if x and y are independent, the covariance will be 0. That is okay. But covariance equals 0 means x and y are independent. This is not always true. But there is one situation they are true where x and y are normal distributions. Okay. This direction will be true only if x and y are normal. Okay. If they are normal and covariance is 0, that means x and y are independent. Okay. But other distributions, it is not true. Both directions will not work. This is a special case. Okay. I think that is what you have been mistaken. But if the x and y, although if they are normal distributions, but if they are dependent, then there will be a covariance term. In that case, you cannot just simply add the two variances. There will be a covariance term. Okay. Right. Let's move on to the next question. Right. So we have this random variable. X is from 0 to 1, and the fx is given 1. When you see this scenario, you should understand that this means the uniform distribution. Right? This means the uniform distribution. Okay. Why? Because uniform distribution, if you have alpha and beta here, beta minus alpha is the probability. So in this case, it is 1 minus 0, 1. So this is a uniform distribution. X is uniform within the interval 0 and 1. From this this random variable x, you have a sample of size 3. And the order statistics, you have named them as y1, y2, and y3. So what is y1? Y1 is the minimum. Y3 is the max. So when you see the order statistics, that means these are the minimum and the maximum, and you have the person in between. So what should be this person y2? What is the value that you can give to this y2? This is the exact midpoint of the ordered data. So that will be the median. Yes, very good. So this is the median, the exact midpoint of the ordered data. This is the order statistics. So part A, derive the probability density function of y1 and y3. That is the minimum and the maximum of the sample. See, derive. You can't just write the equation and get it. You have to derive. Okay, so we did the derivation last time. I'll go back to question number here, 3. So this is the derivation. Okay, derive. So you have to start from this, CDFN for both minimum and maximum. Okay, you have them in your notes. How to get the FY1, capital FY1, and then get the first derivative to get simple y1. And this is capital Fyn, which is the maximum. Get the first derivative and get the simple Fy1. Okay, so that derivation should be there. Okay, so I'm not going to write it again because I have done it, okay, in the previous exercise. So refer to 3. Okay, you have to derive. Okay, and you have to derive and get these answers. Okay, so what do you need? The minimum. Okay, so you have to find the probability density. That means you need Fy1y. So I'll write the equation and do it, but you have to derive it. Okay, if you start your answer from here in examination, you are going to lose marks because you haven't derived. You are just using the answer. Okay, so you have to derive. Okay, there should be this derivation should be there. Okay, refer question number 3. You can find it. Okay, for the max, the min, well, you know how to do it. Okay, refer the notes. It's everything is there. Now, if you do that, okay, can you find the PDF of the minimum? You have fx. Fx is there. You need capital Fx. Well, since it is the uniform density, may I write it? Fxx is, you have to integrate lower bound 0 up to x 1 dx. So that will be just x, right? That will be just x. We'll wait from 0 to x, so that will be x. If you write it in the proper manner, this is how you have to write it. X is 0. When x is less than 0, it will be x. In between 0 and 1, it will be 1 after x greater than 1. So this is our CDF. Okay, and what is n? N is 3, sample of size 3. So let's substitute these numbers. You will get n is 3, 1 minus, what is fxy? Fxx is x, so fxy will be just y to the power n minus 1. 3 minus 1 is 2, and what is fxy? 1. So simply 1. So this will be 3 times 1 minus y to power 2. So this is our the minimum, and better to write it like this. Again, the minimum will be in between 0 and 1. So here's the PDF of the minimum. In the similar manner, you have to find the maximum, Fyn. Again, you have to do the derivative. Okay, you have to do, you have to do the derivation, like in question number 3. And then you'll end up with this one. Right, for the maximum, n is 3. Fx is there. Fxx is x. Fxy will be y to the power 3 minus 1, which is 2, and fx is 1. So that's it, 3y square. So this will be the maximum. Okay, right. So you have the minimum and the maximum now. So here's the min. Here's the max. Okay. So the part A is done. And then we move on to the next part. Suppose the joint PDF of y1 and y3 is, okay, it's given in the statement. So the joint PDF of y1 and y3 is given. Okay, so you are not asked to derive it, it is given. And look at the support. Now these are order statistics. So obviously they are depending, right? See? So this is the joint PDF of y1 and y3. You have to find the PDF of Z1. Now a new random variable. What is Z1? The difference of min and the max. Actually, what is this? What is min minus max? What do you call it? It has a name. Sorry, the max minus min. What do you call it? Let's call the range. Exactly. So you have the range. You have to find the PDF of the range. Let's see. Interesting, right? So how do you do that? Now it's a hint is given. Hint is you have to define a new random variable Z2 as Y3 and find the joint density of Z1 and Z2 to derive the marginal density of Z1. So we are going to use the hint is there to use the transformation method with the Jacobian. Okay, why? When you have Y1 and Y3 and your new random variables are Z1 and Z2, so you can write Y1 in terms of Z1 and Z2, Y3 in terms of Z1 and Z2, and then get the Jacobian, and easily you can find the joint density of Z1 and Z2. But the question is to find Z1 only. You can integrate out Z2 away. You can easily find the PDF of Z1. Okay, so let's do it one by one. So let's follow the steps one by one. So what do we know? We know the joint density of Y1 and Y3. So that is there. So we don't have to worry about finding it. It's given that Z1 is defined as Y3 minus Y1. And we have given a hint to use Z2 to be Y3. So this is our own random variable we define, and it is a simple one. See, just Y3. So our calculations will be very easy. This is like a dummy variable. Now, if this hint was not given, you should be able to figure out if you are going to use the Jacobian. The easiest is the Jacobian in this case, using that transformation method. You should know that I have to define my own random variable. It should be a simple one. Okay. When it comes with min and max, I think the max is the easiest to go with. So defining Y2 to be max is easy. Okay. Anyway, you can try with Y1 also and see how it goes. Okay. Anyway, you have to end up with the same answer, because when you do Z2 to be Y1, when you integrate out, it may cause some complications. Therefore, this is the the easiest way, defining your dummy Z2 to be Y3. But I recommend you try Z2 to be Y1 and see how it goes. Okay, that as a homework. Okay, now what is the next step? We have to find the inverse functions. That means you have to write Y1 in terms of Z1 and Z2, and Y3 in terms of Z1 and Z2. Y3 is Z2 already, so there's nothing to do. What is Y1? Y1 is, if you take this to the other side, it will be Y3 minus Z1, but we know Z1 is, we know Y3 is Z2. So Y1 will be Z2 minus Z1. Now we have our inverse functions. Y1 in terms of new variables, Y3 in terms of the new variable. Okay. So this is found in the inverse function. What is the next step? Find the Jacobian. Right. Now you are very familiar with finding the Jacobian. Dabba Y1, dabba Z1, dabba Y1, dabba Z2, dabba Y1, dabba Z. Dabba Y2. In our case, it is 3, right? Hold on. Dabba Y3, dabba Z1, dabba Y3, dabba Z2. Okay. Substitute them. Y1 is Z2 minus Z1, derivative with respect to Z1. Again, dabba Z2 minus Z1, derivative with respect to Z2. Y3 is Z2, derivative with respect to Z1. Again, Z2, derivative with respect to Z2. Okay, let's do this quickly. The derivative of Z2 minus Z1 with respect to the partial derivative of Z1. So Z2 will act as a constant. So there's nothing coming from that. Negative Z1, you have negative 1. If you move to the next one, Z2 minus Z1, when you take the partial derivative with respect to Z2, Z1 will be like a constant. So that part, the answer, the derivative is 0. So Z2 derivative Z2 will be 1. Then dabba Z2 over dabba Z1 will be 0. Next will be 1. And when you do the cross multiplication, you'll end up with negative 1 times 1 minus 0, which is negative 1. And when you take the determinant, it is 1. Okay. So this is the Jacobian, right? And that will be 1. Okay. So that's done. What is the next step? You have to find the joint density of Z1 and Z2. How do you do that? So you take the joint density of Y1 and Y3, and wherever you see Y3, okay, I'll write it again here. So we know GY1 and Y3 is given. Capital Y3. It is 6 times Y3 minus Y1, right? So here's the joint density. 6 times Y3 minus Y1. Wherever you see Y3, you have to replace it with what? What is Y3? Y3 is Z2. What is Y1? Y1 is Z2 minus Z1. And then you have to multiply it by the Jacobian. So this will be GY1, Y2, we evaluate at the inverses. So I'll just write Z1, Z2. These are the inverses, okay? And multiply by the Jacobian. Okay, so what is your answer? 6 times Y3 is Z1. Sorry, Z2. Y1 is Z2 minus Z1. And the Jacobian is simply 1, right? So this Z2 and this Z2 will cancel out. Negative and negative becomes positive. So the answer is simply 6Z1. Okay. And what is the support of this? Okay. So this will be, because Z1, Z2 is Y3 and Y1 is Z2 minus Z1. So if you do the inequalities one by one, you will see that it is going to be 0 and 1 in between Z1 and Z3. Now I did a similar one in the previous examples, how to find the support of Z, now this joint density. Okay, so this is the joint density. Please refer that. I think it is, which one is that? Maybe in where did I do it? Maybe in the previous example, right? So I did this, how to find the support of the joint density. Okay, you can easily do that by looking at the this one, and split it into 2 and write down what is Y1 and what is Y3, and you can easily get this. Okay. Now that is not the final answer, because this is the joint density. What is our question? Our question is to find the PDF of Z1. So that means you have to get rid of Z3. Okay. Anyway, it is not here, but well, you have to do it. You have to find f of Z1. That means you have to integrate out Z3 away from the joint density of Z1 and Z2 away. Okay. Right. So our joint PDF is Z6 times Z1, T Z2. What is the support of Z2? It will be from Z2 up to 1. So integrate from Z1 up to 1. Z2 is from Z1 up to 1. So that is the limit. So this will give you Z1 to 1. So what is the answer? Z1, Z2 will be from 1 minus Z1. Right. So here's the answer of the PDF of Z1. Right. 0. Otherwise, again, when you integrate out Z2, the support will be now from 0 to 1. Okay, so here's our final answer. Okay. Is it clear, all the steps? Okay, so we have the question, do we have to prove the joint density of order statistics? Now I went through your learning outcomes and it is not there. Okay, you will be not tested on deriving the joint PDFs of order statistics. But if you would like to learn it, it is very easy actually, but it's not there. So we are, I haven't included it in my notes or any of the examples. Therefore, we'll omit it for the exam also. But it is possible. Okay, I will not test you on deriving the joint PDFs. Okay, like this, it will be given if it is needed. Okay, now the question, although it is easy, it's we didn't cover it and it's not actually there, something extra, but you can try it. Okay, there is a method called the heuristic method. I think I mentioned it earlier. It's very easy actually. Just a pattern. If you identify the pattern, you can easily find the joint PDFs of any of the order statistics, not just min and max. The joint density of 1, 2, 3, the first 3 order statistics, the joint density of 6, 7, 8 order statistics. Likewise, you can find any of them. It's very easy. Just search it, the heuristic method for order statistic. You can easily find them, but I'm not going to test it. Okay, just for your, if you're curious about it, you can refer. But that will be not tested in your examinations. Okay, not for this course. Okay, any other questions about this example? So be very careful with the steps. If you follow the steps, okay, you'll end up with the correct answer. Okay, I'll type the name, okay, for you, so you can try it. Give me a minute. Okay, I'm going to share a certain PDF file with all of you. Just refer this one. Okay. That will show you how to find the joint distribution of any order statistic using the heuristic method. Okay. Right. Shall we move on to the next question then? Okay. So here's convergence in distribution. Okay, you have a sequence of random numbers, x1, x2 up to xn, identically independent and identically distributed. And again, you can see what is this distribution? X is what? Now, with all the examples we did so far, you should be able to understand or identify this distribution. That is uniform. Uniform from where to where? Uniform from, yes, uniform distribution. What are the limits? Alpha and beta? 0 to theta. Yes, thanks. 0 to theta. Now, what is the difference between these two? What is the difference between first one and the second one? Parenthesis, square, and another one. So you call them closed intervals and open intervals, right? Closed intervals and open intervals. So what is the difference between these two? So this is also very important. Sometimes it will be given x1, x2 up to xn be IID sequence of random variables, and without giving this fx, they will give you either first one or the second one. What is the difference between first one and the second one? Okay, so Susan, okay, Susanna, you are saying the box bracket, the square bracket contains the exact points, yes. And when will that happen? The exact probability happens when? You are getting closer. Your answer is very, very close. So when you get exact probabilities at endpoints, yes. When will that happen? At discrete, exactly. So you got the answer, Mangi. It is the discrete and the continuous. So first one is the continuous uniform distribution. The second is the discrete uniform distribution. I'm very happy to see that you have understood it. Very good. Okay. So the first is continuous uniform. Second is discrete uniform. Okay. And you know the difference between discrete distributions and the continuous distributions. Discrete, you can have point probability. Probability of 0 is possible. Probability x equals theta is possible. But with continuous, it is not. Only the interval probabilities are possible. Okay. So that's something extra for you to remember when it comes to questions. Okay. Now define yn, which is the max of xi. Show that the yn goes in distribution to 0. Okay, so this is only a part, actually a part of the question, because in another part, a previous part, they have asked the students to derive the distribution of the max for a uniform distribution. Okay. Right. So how do you find the max? Okay, you already know the distribution of the max. Okay, using the, when you have to do the probability, or sorry, the convergence in distribution, you need the CDF. Okay, so you need CDF of the max. Okay, and CDF of max is fx to n, right? Am I correct? Yes, fx to n. The CDF of max is this, and since this is the uniform density, fx will be, sorry, 0, x over theta, 1. Okay, and you know the supports. So this will be, when with y, it is y over theta to power n. Okay, so this is the CDF of max. Actually, the derivation of this was in a previous part of the same question. I didn't include it in this case. So what you can do is, you can say from the answer from part A, the CDF of max is this. You can write it like that and, you know, proceed with the next step. Okay, is this clear? You don't have to derive again. If it is done in a previous part, just refer from part A and proceed. Okay. So when you have to show that the convergence in distribution, you take the limit n goes to infinity, the CDF of whatever the variable you want. So this is from 0 to theta. Okay, from 0 to theta. Anyway, you have to take n downstairs, otherwise you can't have 0, because see, it converge in distribution to 0. So you have to have this limit going to 0. That is what we have to show. Okay, so we have the limit of this to power n, 0 to theta, okay, to the power n. So you have to take this n somehow downstairs. Okay, so what do? You can write this like right. And when n goes to infinity, you have n downstairs in all the time. So you have, if you think about the upper, the numerator, you have 0 at the top, and the same happens with the downstairs. So you have this goes to 0. So which means yn goes in distribution to 0. So whenever you have to show goes in distribution, you get the CDF and rearrange the terms. So you have 1 over n. Okay, that's it. And you will be done. Okay. Now this is, if you think this is complicated, you know how to do it. Get the upside down and take 1 over n. That is also okay, right? Anyway, what you have to do is make this, you have n downstairs. So n goes to infinity, 1 over infinity becomes 0. Okay, that's all you have to do, right? Okay. So the next step, next part. Now you have the sum of the sequence, Tn. Okay, so I mentioned that last time also, when you have T or Sn, that is the sum, x1 plus x2 up to xn. Sum of a random sample of size n with mean mu and variance sigma square. Okay, so you know that it is from a random sample and the mean is mu, variance is sigma square. So what is that mean and variance? Those are the population where the sample came from. Okay, sum of a random sample of size n with mean mu and variance sigma square. So you should understand that. So you have the population. From this population, you took a sample of size n. The population has the mean mu and variance sigma. Okay, and depending on that, there will be some means and variances for the sample. Okay, let's see. Now, what do we know? We know that Tn is x1 plus x2 up to xn. Okay, so you have a problem, 0 over 0. It's not defined, right? It's not defined, but we don't have 0 over 0 here. What is it? Go approaches 0 as n goes to infinity. So this is not 0 over 0. It is just getting closer and closer to 0. Okay. So that's the nice thing about the limits. Okay. So you don't have exactly 0 over 0. What you have is approaching it. So when n goes to infinity, it approaches 0 and 0, but it never touches 0. So that's okay, right? So limit n goes to infinity, 0 over 0 is different from 0 over 0, okay? Because this is a limit, because it's not never going to touch. If you think about the, the point 0, 0, it goes and goes and goes and, it's reaching it, but it never touches, okay? Is that clear? Is it clear now? Okay. So it is not exactly 0 over 0. You are just getting closer and closer and closer, approaching to 0 over 0, but never touches. So no problem. Okay. So here's Tn. Let's go back to the part B. Tn is x1 plus x2 up to xn. And if you divide by n, what do you get? You get the average of this. So let's say x bar n. Okay. So if you take the total and divide it by n, that will be the sample mean. What is mu? Mu is the population mean. Okay. You have the sample mean. Yeah. You have to show that this is what you have to show. Tn minus n over square root of n times sigma, it is an01. What is an? What is an? Approximately normal. Not exactly, approximately normal. Okay. An is the approximately normal to 0 and to 0, 0, 1. That means the standard normal distribution, approximate. Okay. So when you see n, that is normal 0, 1. When you say an, that is approximately normal. Now, whenever you see this double tilde, that is actually approximately normal. So there's no need to put a. Actually, this should be a typo. So this is, okay, let me correct it. When you have this, this means approximately normal. Why you have double tilde? Or in another way, this is an. Okay. Right. So it should be just one tilde. Okay. Sorry about that. It's a mistake. Now you have to show that this quantity is approximately standard normal. Okay. That is 0 mean, standard deviation 1. So let's start with what we know. What do you know? Now this is where you use the central limit theorem. Okay. So you have to mention that from central limit theorem. What do you know from central limit theorem? What is the central limit theorem? Regardless of the population distribution, the sample mean approximates to normal distribution with mean, mu, and variance. What is the variance? Sigma over square root of n. That is the sampling distribution of sample mean. So I'm stating it again, the central limit theorem. Regardless of the population density, the sample mean approximates to normal distribution with mean mu and variance sigma, the standard deviation sigma over square root of n. What is the other thing you have to add? Sufficiently large n. For sufficiently large n. So that is the central limit theorem. From the central limit theorem, we know that x bar, that is the sample mean, is normal with mean mu and variance sigma square over n, or standard deviation sigma over square root of n. So this is from the central limit theorem. So let's use it. What do we know? When you take the mean, sorry, x bar and subtract the mean and divide by its standard deviation, what do you get? You get the normal distribution. So let's use normal because approximation is there. Normal 0, 1. This is from the central limit theorem. So this statement should be there in your answer from central limit theorem. You can't just write it like this. Okay, otherwise you will lose marks if you do not mention this. From central limit theorem, you got this answer. Okay, not out of any blues or not out of thin air. Okay, this is from central limit theorem. Now let's replace what you want. What is x bar? Tn over n. This is Tn over n minus mu sigma over square root of n. Approximately normal 0, 1. Okay. And it is better if you write it from CLT for sufficiently large n. Okay. So we assume that this n is sufficiently large. Okay. And then what can you do? So you have division by n. So that means you can multiply everything by n. So this n will go away. You have n times mu. Okay, so there should be a mu here, another type. Okay, now it's correct. And then sigma over square root of n. You have division by n here. Okay, this n. Okay, so you are going to, you're taking this n. How can I explain it? I'm sure you can understand this, but to make it clear to all of you, I will write it like this. So this n comes downstairs, right? So you have Tn minus n mu, this n times sigma over square root of n. One square root will cancel out. So what do you get? Tn minus n times mu, square root of n times sigma. What is this? Approximately normal 0, 1. Okay. So that's what we want to show. So if you want, you can omit the double tilde, put one tilde and write an, approximately normal. So there should be a mu here. It's a typo in my typing error, sorry. Okay. And there's another meaning for an. I don't know whether you have heard it. Asymptotically normal. Have you heard it? Asymptotic distributions. Okay, so there's another an. You learn it in 203. Asymptotic distributions. Okay. Right. Now, is this clear? How to get the central limit theorem and show what you want to prove? Okay. Right, let's move on to the part C. So you have x1, x2 up to x25. Now your random sample is 25. So you can say large enough. From a uniform 0, 1 distribution. So this is discrete. Okay, this is discrete, where the mean is 1 over 2 and the variance is 1 over 12. You have to find T25 less than 12 using the results in part B. Results in part B. Now you have to incorporate your results, what you have, the answer you got from part B or the answer you proved in part B in order to answer part C. Now what do you have? You have IID, that means independent and identically distributed. What is the distribution? Uniform from 0 to 1. You have a sample of 25. You know the mean and the variance. Okay, so this sample came from uniform distribution. You want to find the probability T25 less than 12. So what is T25? The sum of these xi's, I going from 1 to 25. So the sum of this, you have to find the probability this T25 is less than 12. T25 less than 12. So how do you proceed? What do you know about T25? See, from the previous one, you know that T25 minus 25 times mu divided by, substitute all the values to this, your new example. And then you can proceed with finding the probability. This is standard normal. So you have the standard normal table. You can read it and find the probability. So let's try to do it. Okay. Right. So let's try to write this in our, so what do we know? We know that from part B, T25 minus n mu square root of n sigma. This is what? This is a normal distribution, right? So if you are doing T5 minus something and divide, so you have to do the same for the right hand side also. So the left hand side, you subtract n times mu divide by square root of n and sigma. You're going to do the same for the right hand side. So you do 12 minus n mu. You have to do this. Okay. Now what will happen to this left hand quantity? We know it is normal. So you can write z here. Why? We know from part C, sorry, part B, we know that this is normal, approximately normal. Right? So instead of this whole thing, you can just write z, because it is the notation for standard normal density, less than 12 minus what is n? N is 25, mean is 1/2, divide by square root of n will be square root of 25, sigma is 1/12. Right? So can you do this one for me? Tell me the number you get. Anybody who has the number, please tell me, is it less than or equal? Negative. Negative 1.2. Any other different answers? This should be 12 times, it's 6/5. It's 6/5, yeah, negative, yeah, 1.2. Okay, so get the standard normal table. Symmetric about 0, negative 1.2 will be somewhere here, less than it. You can straight away get this probability from the table. Negative 0.35, is it? Should be 1.2, right? So what is this probability? Anybody? Okay, so let me check. Yes, actually, I was checking whether you're paying attention. Okay. Yeah, so yeah, okay, so this should be square root, right? Sorry about that. Yeah, thanks for the, so this should be square root of 12. Okay, so correct it. So tell me the correct answer. Okay, so point, so let's say 0.35, negative 0. Okay, great. So this should be negative 0.35. Good. Very good. Okay, now, okay, you can try it, right? Read the table and find this probability. Okay, is this clear to all of you? Any questions? So likewise, you can see how the things are relating to each other. You did a certain proof, and then you use it in order to find some probabilities, right? And again, these are, now what is this probability? This is not exact probability. This is approximate probability, okay? So this probability that T25 less than 12, this is, so it's better to write T25 less than 12, it is approximately Z less than or equal point. This is the correct way to write it. Why? This is approximate because this is the approximately normal. Approximately normal. So this probability, what you get is an approximation for the whatever that probability. And you can easily, see that now uniform 0, 1, this is discrete. And you are using a continuous distribution to approximate a discrete probability, right? So you can do that from the, from the, sorry, I distracted with the question. You do this approximation because you are approximating a uniform, you are approximating a uniform probability from the normal. Okay, so that is why you don't put exact equal sign. This is approximately find the probability. Okay, right, and we have a question. Don't we have to do the normality correction? Okay, now with the uniform, now in this case we are using a certain proof from part B, and it is approximation. Okay, so therefore you don't have to worry about the continuity correction. Even if you have a binomial or a Poisson in this situation, you don't have to worry about the continuity correction because we are approximating using a previous result. Okay, you are approximating using a previous result. Therefore, don't worry about continuity correction. Okay, this is an approximation. So don't worry about it. But when you have to do calculations to do the, the probability, the Poisson or binomial probabilities with the normal approximation, in that case, you have to do the continuity correction. This is different. Okay, this is based on an approximation that you have already proved. Therefore, simply writing the approximate probability is enough. Okay. Did I answer all the doubts? Right. So you don't have to worry about the normality correction in this situation because you are using a previously proven theorem. Okay. Any other questions? So let's move on to some questions from 2016. So I'm not going to do all the questions, but I have selected depending on your requests, right? From 2016, I'll write down the question. I may not do all the steps, but I will guide you, right? Then you'll be able to do it. The first question, you have a random sample of size 5. And their corresponding order statistics y1, y2 up to y5. The PDF of fx is given x over 2, 0, x2. This is given to you. The question, you have to find the PDF of y1 and PDF of y5, right? Now in this question, it says find. So I was not asking you to derive, okay? And in that exam paper, I think it was given the PDFs of Min and Max were given, I guess. I'm not sure about it. Anyway, you don't have to derive it. So you can straight away start with the min, the PDF of min. Okay. So if y1, y will be this. Now, if you can't remember this, or if if you are not memorizing it, that's okay. You can straight away derive it and get it. It won't take much time, right? Deriving this won't take much time. N is 5. And you have to find fx. How do you find fx? Integrate x over 2 from where to where? 0 up to any x. So that will be x square over 4, right? So this will be 1 minus x square. In our case, it is y now. Y squared over 4 to the power 4. N minus 1 is 4. Multiplied by fx is fxy, so it is y over 2. Right? So if you want, you can simplify it further, or if you leave it like this, no problem. But make sure to write it in the proper way. We can write 5 over 2 y, write it simply in a nice manner in order, 0 otherwise. And then in order to find the max is this. We have 5 times y square over 4 to 4 y over 2, right? So that will be now. If you do not rearrange the term and leave it like this, that's also okay. No problem. You won't lose any marks. Okay, this is just to make this answer nice. Okay. So you have to write you have to find the PDF of the min and the max. The next step, you have to find the expectation of part B is you have to find the expectation of y5 and variance of y5. Expectation of y5 and variance of y5. Well, how do you find it? You take the density of y5 multiplied by y. Y5 is the maximum anyway. The random variable is y. Okay? So you integrate it from 0 to 2 is the support. Right? So do that. Okay, I'm not going to do all the steps. You know how to do the integration. This is a very simple one. And if you do that, you'll end up with let me write it like this. Okay, so do this simplification and you will find that it is 1.818. Try this, okay? Try the integration and see whether you can find this answer. And in order to find the variance, you have to find the second moment expectation of y5 square. So you have to do y square times fy5. Okay, and the same thing, 0 to 2. And you'll find that it is 3.33. And from that, you can find the variance of y5 or the max. That will be, you know, the computational formula of variance. So that will be this. Okay. And see whether you can find the answer. I got 0.0275. Okay, see whether you can find that also. So these are not hard, right? Finding the expectation variance when you know the PDF, it's not hard. Then you have to calculate probability y1 less than 1. Okay. Again, it's not that hard. If you want, you can use fy11, okay, because this is the definition of the CDF, or you can from 0 to 1 you can integrate fy1. That is also okay, right? So you can use either this way or this way, right? This way or this way. Doesn't matter, you will get the same answer. See whether you can find this answer, right? Since you have the fy1, this one, you can integrate it from 0 to 1 and check it. Or you know the CDF of the minimum and just substitute value 1 for y, and easily you can find it, right? I think this using the CDF is easy because you know this is right. So it's 1 minus y to the 4 to 5, right? So you can easily find this probability. Right. Okay. The next question is a transformation. This is something I guess most of you have asked about this question. Okay, so I have a question, Tarini. When getting normal distribution by adding two normal distributions, if those two are dependent distributions, can calculate mean by adding those two normal means, or should we only add when two normal distributions are you mean I think independent, right? Already the identically distributed if they are normal. For the means it's okay. Okay, for the mean, adding mean, it is okay to have the dependency. The problem comes with the variance. Okay, so therefore you cannot simply add both mean and variance if they are not independent. If they are independent, adding the means and the variance, you can go ahead. But with the dependency, means will be fine, but the variance, you have the covariance step. Okay. Okay, so here's the second one. This is about the polar coordinates and the Cartesian coordinate transformation in between these two methods. Okay, so you can generate a point at random in a plane according to the polar scheme or polar coordinates. How do you do that? You choose the radius r. Okay, I'll draw the Cartesian coordinates. You take the origin. Now here's our point. Okay, here's my point, x and y. So this is x, this is y. How do you define the polar coordinates for this one? How do you define the polar coordinates? You find the distance from origin to this point. This is the radius, and then theta from x-axis to the line that you got the radius. Okay. So this point, let's say P can be represented as in Cartesian coordinates x and y, or it can be represented as r theta. So this is the polar coordinates. This is the Cartesian coordinates. Both are it's the same point in two different methods. So in this question, you have to do a transformation in order to find the marginal density of this r and theta. Okay, so this is the question. So you have these polar coordinates. So you define t to be r square. R square is the square of the radius. Okay, now this follows a chi-square distribution with degrees of freedom 2. Okay, and then this r is the radius. Okay, and then independently you have the theta. Theta follows uniform distribution, and you know it is from 0 to 2 pi, right? The radius measured in radians. The theta can be any value from 0 up to 2.5, the whole circle. Okay, so theta follows uniform 0 to 2.5, and our r, in this case we define r square, that will be chi-square distribution, degrees of freedom 2. Now you are familiar with the uniform distribution, and this exam, the PDFs of the uniform distribution and chi-square distributions were given in a supplementary table. Okay, so you don't have to worry about Okay, if you panic, okay, what is chi-square? What is the distribution? What is the PDF? You don't have to worry. That has been given as a supplementary table at the end of the paper, so you can easily find the distribution of T. Uniform, well, it was also given, but you know it is anyway. You know how to find it. Okay. The question is to find joint distribution of X, which is R cos theta, you know that, and Y, which is R sin theta. That also you know. Okay, so you know your X is, okay, here's your X, you get it from R cos theta, and here's Y you get from R sin theta, right? So that we know. Right. So you have to find the joint density of X and Y. The polar coordinates are there, their relationship, you know, and it is also given. You have to find the joint distribution of X and Y. So how are we going to do this? Right. Again, we are going to use the Jacobian, okay, and do the transformation. Okay, so this is how we are going to do it. This is actually a standard way of doing it. Okay, so you can find the answer for this one very easily in internet. Okay, a lot of documents are there actually showing this proof. Anyway, I'll do it for you and explaining step by step, right? So if you want to find the distribution of X and Y, what is the first thing you need? The given random variables. What are the two given random variables? The given random variables are T and theta, and their distributions are given, and you know they are independent. So how do you find the joint density of T and theta? How do you find the joint density of T and theta? They are independent, so multiply the marginals. Yes, so first let's find the marginal density of Ft. Ft is what? R square. What is it? It's chi-square 2. And from the given information, you can find that it is this. Okay, so how you got this? It was given in a table. At the end of the paper, it was given in the table how to get the chi-square 2 distribution. Okay, so you can find it. And then how do you find F theta? It is uniform, right? So it will be 1 over 2 pi, okay, from 0 to theta. So you know Ft and F theta. And since they are independent, since T and theta are independent, you can write their joint density. That means you multiply the marginals. So what do you get? Very simple. E to the negative t over 2 divided by 2 times 2 over 5, so 4 pi. Since they are independent, the supports will be t going from 0 to infinity. Why? Because this is the radius. You know, it can go up to infinity, no problem. And then theta from 0 to 2 pi. Okay. Right. So this is our joint density now. So in previous examples, joint density was given. Here, the information was given, so you can derive it. Independence is given, the marginals you know, so you can find the joint density. So we find the joint density and leave it there for a while. We need it later after you find the Jacobian in order to use the inverse functions and find the final the joint density of X and Y, right? So we leave it there and move on to the next step. What is the next step? Finding the inverse functions. So what do we know? We know that X is R cos theta. And we know Y is R sin theta. Now what is our goal? We have to find R and T in terms of X and Y. We have to find R and T in terms of X and Y, the inverse. Okay, so how do you do that? Now for this, you need a little bit of trig knowledge, right? So we expect that you have this knowledge in the trigonometric. So whenever you see this R and sine, the first thing that comes to mind is cos theta squared plus sine square theta plus cos square theta. That means their squares are 1, right? That is the a rule that we are very widely used, and most of the time we use it, and very common identity in trig. So that's what we are going to use here. Okay, we know X is R square cos square theta, Y is R squared sine square theta. So we get r square this, and from trig identities we know this is 1. So x square plus y square is r square. So you have one identity or one way to write x, y, and r. The next is to incorporate t. How do you incorporate t? Sorry, t is r. So this is actually t. R square is t. So we know the relationship between x, y, and t. What about theta? How do you define the relationship between theta and x and y? It is from this r cos theta and r sin theta again. So you know sin theta divided by cos theta, that is tan theta. Yes, you have to get the tan theta. So that means y over x, that is the next identity, which is r sin theta over r cos theta. So r cancels out and you get sin theta over cos theta, which is tan theta. So that means, so t is x square plus y square, and theta becomes tan inverse x over, sorry, y over x. So these are the two equations you are going to use as the inverse, right? T or r square is x square plus y square, and theta is tan inverse y over x. Now we can find the Jacobian, right? So let's find the Jacobian. Okay, so t in dabba dx, dabba y, theta, dabba x, dabba theta, dabba y. Okay, so what do you have? T is x square plus y square, dabba x, again dabba x square plus y square, dabba y. Theta is tan inverse y over x, dabba x, again tan inverse y over x, dabba y. Okay, now again you will need a little bit of trig knowledge here. So y is like a constant when you get the derivative with respect to s, the partial derivative. So you'll get 2x from the first one, 2y from the next one, right? So these two are the partial derivatives. Then what about the tan inverse y over x? So this again, actually this information were not given in that exam. So these are the trig identities. You have learned this in A levels. So we assume that you can remember that. Okay, the tan inverse, the derivative of the tan inverse. Okay, right. So if you do this, what is the answer? You get 2x times negative x square plus y square minus 2y square x square plus y square. Right. So if you do this, common denominator, negative 2 square minus 2y square it's gone, and this is the absolute value. So the Jacobian is 2, negative 2 absolute value, so you get 2. Okay, now look at this leisurely and go back to your trig notes, okay, and check this one, right? Now we have to use the previous answer, the joint density of t and theta. So let's write it again here. If t theta, we know that it is e to the negative t over 2 4 pi. Okay, let's double check. Yes. Now what do you have to do? Instead of t, and this is ft, then we have to write fxy. That will be ft theta at the inverse of this multiplied by the Jacobian. Okay, so that will be e to the negative. What is our t? T is See, from 1, x square plus y square. So we replace t with x square plus y square divided by 2 divided by 4 pi. Now theta is not there, right? So this is our answer. For the joint density of x and y. And what are the values of x and y? And now this is the polar coordinates. So you know that this is from negative infinity, sorry, the Cartesian coordinates. So x and y can have values negative infinity up to plus infinity. Okay, you don't have to worry about deriving the limits because it is already given. Then it is the Cartesian coordinate and the polar coordinate. So x and y, the limits will be the whole real number line. Okay, so this is your answer for the joint density of x and y, and that was the question. It's not asking about the marginal densities, so you are going to stop from here. And then you have part B. Part B is, are x and y independent? What do you think? And then it asks, identify the marginal densities. Not to derive. Not to derive, identify. Any guess? Now, if you want to show whether the joint density is, the margin, if the x and y are independent, what is the shortcut? What is the shortcut that you can use to check whether two variables are independent from the joint density? Yes, exactly. You have to split it. Okay, if you can split the joint density, so one function contains x only, the other function contains y only. Shall we try it? You can very easily do that. Right? You can do this. I'll write it. These are the exponents. So you split it, you add them together, right? So the negative distributed, and then you can write 2 square root of like this. So you have e to the negative x square over 2 times e to the negative y square over 2 over 2 square root of y. Okay. So can any of you identify this distribution? See, so you have split it into fx and fy actually, right? So two functions. Can you identify these two distributions? Oh, hold on, we didn't multiply by 2, right? So, okay, so you have the Jacobian 2 here, and then you have this, and you have the square root here. So now it is okay. Right. We missed the Jacobian multiplication by 2. Right? So 2 cancels out. So you have the square root of 2 pi. So what is this? What is this distribution? Anybody who can identify? These are the standard normal distributions. Yes. What is this? Is standard normal. Why is standard normal? So now you know how what is the relationship between polar coordinates and Cartesian coordinates, right? So you know the relationship now. They are standard normal densities, and therefore you can easily say these are the marginal densities of x and y. Okay. So it's nice, right? How you draw this bridge in between statistics and mathematics. These polar coordinates and everything, these are mathematics, and then you find their distributions, right? That comes with statistics. So all these things are related together. Okay, is this clear to all of you? Any questions so far? Okay, so let's try. Okay, so I have a question. Do we have to memorize F distributions, student key, chi-square? No. Okay, you don't have to memorize them. If you have to use them, as I mentioned, those distributions, if you need the moment generating functions, they will be provided as supplementary tables. Okay, you don't have to memorize them, right? And the properties for this 201, we have to just to introduce them to you, but we are not testing them because you will need it in 203. Okay, so the instructor will ask you, have you heard about F distribution, T distribution? So you can say yes, because you have heard that in 201, but we are not doing any calculation or anything here, just to introduce them. But you will use these distributions in next course. Okay, so here we are just introducing them, give you an idea about these distributions. Okay, you don't have to memorize any of them. Okay, so let's try to do an approximation and a central limit theorem one. Okay, this is from, okay, so 3B in 2016. Let's check 3B. Okay, so that one is, it will take a lot of time. Okay, the Poisson distribution, the binomial and the Poisson one. What if I share the answer with you for this one? Is that okay? If I'm going to start it, I won't be able to finish it at 7:30. Okay, because it's a little bit lengthy, and I will do maybe I'll do a small video on that one. Okay, whatever the questions I won't be able to finish today, I'll prepare another video and upload it. Okay, because it will take a lot of time. So therefore, we'll do another example from central limit theorem and approximate. I think it's better to do the tute number 4, I guess, because most of you have asked about it. Tute number 4, which contains the normal approximation, right? Let's check it. Okay. Give me a minute to get the tutorial number 4. Okay. But before we go into that, asking question number 4 C part. Okay, so let's do question number 2, question number 4 C part also. Okay. Okay, so let's do 2019 question 4. Write it down for you. Only C part, or yeah, maybe let's do the C part. So you have xi random a sequence 1 up to n independent Bernoulli trials with success probability P. And it's given that yn is sum of xi, I going from 1 to n, 1 or n. So this is the mean actually, right? We have the sum divided by n. So this is the sample mean. Okay. The first thing you have to show that this quantity in the left-hand side Gaussian distribution to normal with 0 mean and variance P1 minus P. You have to clearly state the theorems used in the proof. Okay, so this is part 1. Okay, so let's try this one. So what do we know? We know we have independent Bernoulli trials. Okay, independent Bernoulli trials. What are Bernoulli trials? Binomial is when you have n number of Bernoulli trials. Okay, Bernoulli is just one trial, success or failure. Here it says the success probability is P. If success probability is P, what is the failure probability? Failure is 1 minus P. Okay, so that is the Bernoulli trials. And it says that they are independent, and they are all by Bernoulli, so they are IID. Okay. Right, so we have to show that the yn, what is yn? The mean. Okay, the yn is sum of xi divided by n. Okay, now what do we know about the Bernoulli distributions? So you have a random sample of sample size n. Now if you take sum of xi's, just the sum, Tn, we know that if you have n number of Bernoulli trials, that is the binomial distribution. With n number of trials, P the same probability of success. Now this is the key thing you should, you should know. Okay, so this you should know from ST102. You have independent Bernoulli trials. When you have n of them, that becomes the binomial. Okay, so that is how we define a binomial distribution. Binomial distribution is a collection of independent Bernoulli trials. So this you should know to start with. Okay, and then we know it is given that yn is this sum. What is the sum? Tn divided by n. So this you get from the given information. This you should know. Okay, so we assume that you know this, the connection between binomial and the Bernoulli trials. Okay. Now then you have to use the central limit theorem. So whenever you have the means and look at this, the distribution, you have the mean and the standard deviations, you should know that comes from the central limit theorem. So wherever you have mean, the variance, the normal distribution, that means it is the central limit theorem. So what do we know from the central limit theorem? Central limit theorem says the mean is approximates to the normal with what is the mean will be the population mean, and then the variance will be the population variance. Now what is our population now? Our population is this binomial distribution. And we know that for binomial distribution, what is the mean? Mean is n times p. And the variance is n times p times 1 minus p. So this you know from previous courses. And in this, let me check in the exam paper. No, it's not given, right? So it's not given. So this you know from the previous courses. Okay. Now from the central limit theorem, what do we know? The sample mean. What is our sample mean? Sample mean is yn, right? So we know that for sufficiently large n, so what is our x now? X's are, so I'm going to write Tn here, right? So that's for the binomial density or this sum. Okay, so Tn minus np. What is this? The mean divided by the standard deviation. This is from the central limit theorem, right? Okay, so you get the mean. You get the sum, which is you get the sample mean, which is Tn over n. Okay, you can write yn here, right, straight away. Can we write it? Hold on. No, the Tn, right? Tn is the, okay, so Tn is the binomial density. Okay, so the Tn, and when you subtract its mean np and divide by its variance. Okay, so that is approximately normal with the standard normal density. Okay, why? Because Tn is approximately normal with mean np and variance np1 minus p. So if you subtract the mean divided by the standard deviation, you get the standardized one. Okay, so this is the approximately normal. Okay. Now you take yn. What is yn? Yn is Tn over n. And that means Tn is n times yn. Right? Now you can write n times yn. N times yn is Tn, and what is Tn? You already know it is this. See, this is the same thing. So you can write, instead of Tn, you can replace it with n times yn minus np, np1 minus p, square root, approximately normal, 0, 1. Okay. And let's go and see. We need square root of n outside and yn minus p. So that means we have to get rid of this n. So let's take it outside. Let's take this n outside. So you have yn minus p, square root of n, p1 minus p. Nothing is going to change from the bottom. Still, it is approximately normal. Okay. So from the bottom square root, now if I write it like this, the bottom I can write square root of n separately and this p times 1 minus p square root separately. So one square root you can cancel out. Okay, so what do you have? Here we are getting closer. See, now we get square root of n. Square root of n, yn minus p, p1 minus p. This is approximately standard normal. Right, and then what can you do with this standardization? This standard deviation, you can multiply it from this, the standard deviation you see on the right hand side. Okay, so this is another nice trick that we do. You keep the mean as it is, so it's still 0, and instead of the standard deviation, you replace it with this, and now the standard deviation, when you write the normal, it becomes the variance, so the square root goes away. This. Okay, so you have square root of n minus p, it is approximately normal, 0, p1 minus p, and that is exactly what we have to show, goes in distribution. So you can write n minus p goes in distribution to normal, 0 mean p1 minus p. And even you can go one step ahead, and sometimes the question may be like this. The question may be to say square root of n goes in distribution to normal, no, you can't do that. Sorry, you can't do that because you have the square root of n outside. So let's leave it like this. Okay. Right. So this is how you prove it, right? Because if you don't have anything in front of this square root of n is not there, you can take this p to the mean. Okay, but here you can't do it. You have the square root of n outside. So this is how you do it. Now, in the trick here is you should know that when you have Bernoulli trials, their sum becomes the binomial, and the mean of the binomial and variance of the binomial. And then when you take the sum, you have this central limit theorem, which goes to the mean and the standard deviation, the approximation, the normal distribution. So that's all you should know. And then after that, after you formulate this normal approximation, the rest, it's simply substituting the letters that you want in your final answer. Okay. So that's part 1. What is part 2? Okay, part 2 is the approximation. Okay, I think we can do that also. We'll do that quickly. Part 2 was the college knows from past experience that 30% of students admitted to first year courses will actually attend classes. So the success probability is 30%. So that is P. If 450 were admitted, that is N, approximate the probability more than 150 students actually attend the class. So this is what you have to approximate. And it says, state the assumptions and conditions in order to apply this approximation. You are asking why there's no standard deviation. Are you asking about this? We have cancelled that square root n to the 1 of n. Okay, and when you are multiplying, the bottom goes here because it is the standard, you divide, okay, standard deviation, and so this goes with the mean, okay. So, right, so now if you want, you can take this 1 over n downstairs and have yn minus p, okay, but in this example, you have square root of n with the yn minus p in the answer. So therefore, we are not taking it down and, you know, multiplying the standard deviation in the normal distribution, okay. You simply move the standard deviation over the bottom part. Okay, that's because we need the answer in that format, okay. But if you had the square root of n at the bottom, you know, here, and then you can move it here, then this square root of n will not be there, and your mean will be something else, right? So, like now, that means you can have different ways of writing the same question, okay, even because from the question you asked, now I can give the same question with a different way to, you know, prove the distribution by rearranging these terms, the square root of n downstairs, then you will end up with a different answer, okay. So but in this question, square root of n is with the answer, the left hand side, so you are not moving it, okay. Okay, so here's, let's move to that approximation. So you have to approximate x greater than 150 according to the binomial approximation. Now here you have to use the continuity correction, and also the we have to check the conditions. Okay, so this is the normal approximation to binomial. This question is about the normal approximation to binomial. Okay, so you have to check the conditions. What are the conditions? The conditions NP, both NP and n times 1 minus p should be greater than 5. Let's first check it. Now, what is the binomial distribution here? The binomial distribution is n is 140, p is 30%. Therefore, NP is 450 times 0.3, okay, which is 135, obviously greater than 5, so that's okay. N times 1 minus p is 450 times 0.7, so that is even bigger, so that is greater than 50, that's also okay. So the conditions are satisfied. Now, using the central limit theorem, what do we know? You can approximate x with the normal distribution mean NP and the variance NP 1 minus p. Okay, so that's the approximation, right? So what is NP? We already found it. It's 135. What is n times p times 1 minus p? That will be 450 times 0.3 times 0.7. You will get 94.5. Okay, so this is sigma square. This is of the normal approximation. Now let's do the approximation. Probability x greater than 150, right? So that will be probability x greater than 150 plus 0.5, that is the continuity correction, okay? So Yes, I did the correct addition. Let's double check. So if you have greater than, just greater than, not equal, so you have to add 0.5. Right, so let's do it. Now when you do the approximation, what will happen? Your Z will be 150.5. That is the continuity correction. You subtract the mean. What is the mean? 135 divided by the standard deviation will be square root of 94.5. Right. So if you do that, you will find it is Z greater than 1.59. So you get the standard normal table, symmetric about 0. Here's 1.59. Somewhere here you need the right tail. So read the table and find this. Since you have only the left tail, you will get only the left tail. You can do the symmetry, read negative 1.59. So this is the same thing. These are same. If you do that, you will get 0. And this is approximation, okay? It's approximation, 0.0559. That will be the answer. Okay, even with the Poisson, this is the same thing you do. In Poisson, your mean will be lambda, 1 over lambda, and the variance will be lambda, again the lambda square, right? The standard deviation, square root of lambda, standard deviation. Okay. Is it clear now, part C 1 and 2? Okay. So what I'm going to do next is, do you need another discussion, or may I put the rest of the questions and the tutorial number 4 as a video session? Or do you need a live discussion? What do you prefer? Tell me quickly, 7:34. Would you like another live discussion or a video? We'll see, okay? Good to have a live discussion. So are you okay with doing another one next week, next Thursday also? Do you have any lectures next week? Next semester lectures, practicals? Or can you handle a discussion? Okay, so then let's try to do a live discussion, maybe the last one. So I'll try to do the rest of the questions from 2019 and tutorial number 4, okay? So again, next Thursday, 5:30, 7:30. Try to log in exactly at 5:30 so we can start straight away, okay? Any other questions before we finish? Okay, then I'll upload the video and also the PDF of this worked examples so you can go over them leisurely.